So when we consider the Wittig reaction, we can consider the stereochemistry. And we will see that experimentally it's been determined that if you have a generic simple Wittig reagent, just something with carbon and no special carbon units, you'll typically get the Z alkene as your predominant product. For example, if we take this with we'll have one methyl group and one hydrogen on our Wittig reagent, we're going to see that those methyl groups will be pointing on the same direction. This is the Z alkene. So with normal Wittig reagents, that's what you get. But we're going to see if it's stabilized. And by stabilize, it means that the C minus, the negative carbon, can resonate somewhere. Either we have an electron withdrawing group, or we have a benzene ring, or some other way to stabilize the carbon. We will predominantly get the E alkene. And so, for example, if you take that same aldehyde, and we've got now carbon with a benzene on it as our reagent, Wittig reagent, we will actually get the opposite stereochemistry. We will get the E product instead. Notice that our bulky groups are trans to each other, but remember E and Z refer more to atomic number, but really we mean cis and trans here. So because typically those two are the same, right? Z usually means cis and E usually means trans. So we see those same patterns happening here. So with this, we're going to end up having preferences for one or the other depending on how we stabilize our reagent. And so factors that stabilize, the stabilizing factors are electron withdrawing groups, so nitros, ketones, esters, anything that's got an electron withdrawing component. So all of our strong deactivators and moderate deactivators from EAS would work here. Or we have aromatic rings. Just somewhere that the negative charge can resonate to. Because remember, we sometimes will draw the reagent as such, as the ylid form. And now that we see that we have that carbon minus, we can resonate it, right? We can say, I want to move that into the ring for some reason. I want it to go over here to chill out for a bit. It's just delocalized. It stabilizes it. So having it now conjugated to something allows for resonance stabilization. And so that'll stabilize the ylid, which will allow it to get into that E conformation before the reaction takes place. So it's again kind of a kinetics thing. So kinetically speaking, the Z is your kinetic product here. You're going to end up getting the faster formed one, which happens to have the two methyl groups on the same side. And so even though it is sterically less favorable, thermodynamically less favorable, it is formed faster. So by stabilizing your ylid, you tame it down a little bit, giving it some time to get into the right conformation so that you can get the more stable product. And again, heat helps. So I'm just going to erase these resonance arrows because we don't really need to show the resonance, but that's why this is a stabilizing factor. And of course, if you have something like a nitro group or a ketone or an ester, all of those will work. Speaking of esters,